All right, so today we're gonna continue our discussion of anomaly. This is going to be the last lecture on anomaly, and we will review what we discussed about chiral anomaly, and then talk about scale anomaly, connected to normalization group and beta functions. And finally, I'll end on a little bit of reminding you of what we did to in QFT1 when we discussed representation theory of Poincare group. So we organize our fields in terms of Poincare group representations. If we want to discuss conformal field theory, we'll have to redo that for conformal group, right? So we'll have to organize everything in terms of conformal group, and I'll discuss a little bit more detail. I'll give you a little bit more detail about how we go about constructing representation theory for Lie algebras, and then we'll continue with the conformal algebra next week. So this is all going to be working towards a formulation of quantum field theory that does not rely on actions, right? So what we said was that, okay, using Lagrangians and actions, it was we had the massless free fields as a trivial theory. Then we found a bunch of other fixed points within perturbation theory, but mostly for large n, right? These were the Wilson-Fisher fixed point type of things. We discuss a case. Well, okay, yeah. So that's what we've discussed. So we're gonna today discuss scale anomaly, start moving towards discussing a non-perturbative formulation of conformal field theory. Well, we're not going to do that today. We're going to just review the Lie algebra and representation theory of conformal group and work towards that. All right, if there are any questions at any point, ask. So chiral symmetry standard model was the discussion of the last week. Chiral, let me say chiral anomaly or absence thereof, right? Okay, so what was anomaly? Anomaly was when you had a classical symmetry, a symmetry or invariance of the classical action that was not surviving in the quantum world, and we call it anomaly. Global symmetries could be anomalous. That means that the measure is not preserved, so it's no longer a unitary transformation. Gauge transformation cannot be anomalous. That sounds wrong. It's just the theory doesn't make much sense. But today, I'll tell you a little bit about what's called anomaly inflow. I'll just give you a hint. Even though if you have a theory that has gauge invariance that's anomalous, you don't have to necessarily discard it right away. There is a way of thinking about anomalous gauge theories as the boundary theories of higher dimensional ball theory. So that's called the story of anomaly inflow. I'll give you a hint. That's the way towards construction of topological quantum field theory. If you were here last Tuesday, this Tuesday for the seminar, I just want to give you a hint because we had a seminar on this, and you'll hear from time to time about topological quantum field theory. All right. Okay, so in standard model, we had an SU2 left coupled to left-handed Majorana. In particular, well, more important than this, in the standard model, we had the massless fermions, right? So every time you have massless fermions, before it's massless, then you do spontaneous symmetry breaking, you get massless, but the theory, the action is massless. You could have chiral anomaly because we discussed QED, massless QED has two transformations, right? Two gauge invariances. There is a vector transformations, there's the axial transformations, the distinction being in the gamma 5. So how they treat the Dirac, how they act on the Dirac spinner, right? Because the representation from massless fermions, the Dirac spinner is reducible, right? This gamma 5, well, how it acts, right? Anyways, so standard model has SU2 left times U1 one hypercharge times SU3 color, and we had coupled to massless fermions, right? Let me just write it this way. I think this is easier. So the gauge transformation of a Majorana field is like this, right? The left-handed side, the right-handed side. The star is because of the fact that you build the right-handed side by the fact that it's its own antiparticle. The action is classically invariant, but the question was, does the theory survive does this invariance survive quantization? So chiral anomaly must vanish, or the theory, as we discussed it on its own, is nonsensical. Luckily, this happened in the case of Salmon model. So our discussion of anomaly, we did it at the level of Feynman diagram. We did it at the level of path integral using the so-called Fujikawa method. So I'm just going to review the Fujikawa method. Gamma 5 matrix is this identity minus identity in this particular chiral basis, right? In 2D, it's just 1 minus 1, right? So here's a vector transformation. Whoops. No, this is correct. Here's a vector transformation. Here's the axial transformation. They're both redundancies of the classical action. And if you vary the action, you get this term, but then use the integration by parts and the fact that del mu of alpha is 0, you get a boundary term that vanishes. Keep this in mind, right? When we say the action is gauge invariant, or in the case of global symmetries, you're always discarding a boundary term. That's important. All right. Transformation of the measure. So the action is invariant. What remains to be done to check is whether the measure d psi bar is invariant. Well, we take these psi's and expand them in the eigenfunctions of the Dirac equation, right? So phi m and phi bar m. Do you guys know why there is a pair of them? Again, because the transformation is reducible. Yeah, it's a reducible transformation. So there you have a pair of these guys. So you end up with DAM. It's good to play around with this and get used to what gamma 5 and these or psi bar mean. DAM and DAM prime. These are Grassmann variables because these were just the eigenfunctions of the Dirac equation, and psi's are anti-commuting fields, so these are Grassmann variables that we'll have to do Grassmannian integrals. But hopefully you remember that from QFT1. Under the transformation, the gauge transformation, you're going to pick up a Jacobian, and the Jacobian is going to be log of this J is going to decide, or log of J minus 2 is going to decide what is the correction term, anomaly term in the action, right? And then you could put that, you could view that as the right-hand side of the conservation law, del mu J mu, right? All right, axial anomaly in D equal 4. We discussed this, that under an axial gauge transformation, these AMs go to AM plus sum over NCMN. So there are these matrices. These matrices are nothing but traces of gamma 5 integrated against, trace of gamma 5, right? Integrated against this alpha of x. And what you have to calculate is the determinant of 1 plus c. You can view that as exponential trace of log of this and you approximate this by exponential of trace of c. So we're going to be after trace of c. Trace of c, well, let's just for now ignore this bit, this integration part. What we have to calculate is trace of gamma 5, right? But this trace of gamma 5, yeah, okay, so I wanna say it a little bit differently. Yeah, anyway, so let's just say, let me not put equality here. So this part is just this is what we're calculating. The sum over n runs over infinite values, eigenvalues of the Dirac equation, right? These sums blow up. There are infinite of them, right? So you have to regulate it. What are we gonna do to regulate? We're just gonna put e to minus lambda squared over m squared, lambda being the eigenvalue of the Dirac equation, right? In front of it to regulate this. So we put some Gaussian in front of it to regulate this. We're gonna do this regulator in the limit of m going to infinity. So take this expression, expand it, and a large M. So here's the zeroth order term, the first order term, second order term. This minus d squared plus e over 2 sigma mu nu f mu nu is just the expansion of id slash squared. Hopefully remember that, right? What is sigma mu nu? It's a commutator of gamma matrices. It's the way what we did to build representations of the Poincare group, Lorentz generators. All right. So the first term vanishes because trace of gamma 5 is 0, right? Gamma 5 is just identity minus identity. So we'll have to go to the next order term. As a matter of fact, it's easier to organize all these terms in terms of powers of f mu nu, because every term that doesn't have f mu nu will just vanish. Trace of gamma 5 is 0, right? So let's consider the first order term in mu nu and then the second order term. The first order term in f mu nu could be written elegantly in this form. Now in d equal 2, gamma 5 sigma mu nu is 2i epsilon mu nu, the antisymmetric tensor, and this identity is just an identity satisfied by gamma matrices in 2 dimensions, right? Do you remember what gamma matrices in 2 dimensions were? Sorry, Paulus, yeah. Log of j it just becomes this expression becomes epsilon mu nu f mu nu. The e comes from this here, and you end up with this expression for anomaly in 2 dimensions. In 4 dimensions, this term vanishes because trace of gamma 5 sigma mu nu is 0. So the order f mu nu term vanishes. That was expected. Why? Dimension counting, right? Dimension counting. To the next order, we'll have to go to the next order. We're dealing with trace of gamma 5 sigma mu nu sigma lambda rho, because the second order in f, and every f comes with a sigma. All right. This is Dirac algebra tells you that this is the result of it, minus 4 epsilon mu nu rho lambda. It's a totally antisymmetric tensor, and this is the result of the anomaly. It's an integral over f mu nu squared, contracted this way. This term was precisely the dimensionality of this is the axial anomaly, right? The dimensionality of this term is d, right? So whatever I put here has to be dimension d. This is nothing but that other gauge invariant term that we discussed as a topological term we could add to the action, and this was the related to CP bracket. This was a CP violating term, right? This is the F wedge F term in 4 dimensions. All right, any questions? Yeah.
It's not like specifically vector kind of, if I just replace the number by
Yes.
where would this change? Like,
Oh, there won't be an anomaly. You could explicitly check. There will not be an anomaly. You'll have to repeat the calculation, but you'll learn that there's no anomaly. What we did check, not using Fujikawa method, but we checked using Feynman diagrams that the one loop anomaly vanished, or vectors, part of the gauge transformation. That will always survive. So there are 2 independent gauge transformations. One of them fails. We usually call the one that fails axial. You could rearrange things. You could not preserve both of them unless you have anomaly cancellation. What we arrange for anomaly cancellation, but that will depend on your matter content. You'll have to tune your matter content, like as in standard models for anomaly to cancel. Good. All right. Any other questions? All right. Now, this whole analysis that we did was abelian. This was a QED in four dimensions, massless QED in four dimensions, massless fermion QED4. QED has fermions. Massless QED4. But what about non-abelian gauge theory? In non-abelian gauge theory, every step of you could use Fujikawa method. Everything goes through. The only step that you have to figure out, this comes out. But these gauge transformations are now coming, like they are Lie algebra valued. So you're dealing with the generator, the Lie algebra generators, right? And if you go through the whole thing, you'll learn that there's this extra coefficient ABC, which is trace of T8, the anti-commutator of TBTC. Now, importantly, this is totally asymmetric, totally symmetric in ABC, right? And that was important because it cuts down the number of anomaly terms we have to calculate. And we checked, or you have, or will check that these anomalies vanish in standard model. You also have to be careful because you have to check anomalies for global symmetries as well. There are all sorts of global symmetries. Name a global symmetry in standard model. Sure. I mean, that's a discrete symmetry. Well, think about it. All right, good. Any questions? Consider SU2 cross U1. Now, the Lie algebra generators could be either U1 generator, which is basically it's just a phase, right? And a charge Q, which label representation, or it could be SU2 generators Pauli matrices over 2. We have 3 anomalies to calculate. Q, Q, Q. This is U1, 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 right? This is A1, 1, 1. Hopefully you remember what this meant. A1, 2, 2, right? This is the anomaly of Q, TA, TB, and 2, 2, 2, TA, TB, TC. This term vanishes. Why? Always vanishes. Because if you calculate the anti-commutator of Pauli matrices, it is proportional to delta AB. That means that what you're calculating is a trace of TA, but you're traceless because it's SU2. Right? So this term, is vanishes. This was more complicated to calculate. This was also more complicated to calculate. Good? Questions? I just said this. Importantly, A122 and SU2 times U1 is not 0. There's an anomaly. So T8 TBTC is proportional to delta AB. There's a half that comes out, trace of Q. Now, consider, for example, standard model, where this is the U1 of standard model, and these are SU2 lefts, right? What runs in the loop? Whatever runs in the loop has to be U1 charged and SU2 left charged. So what's in the matter content of standard model? That's SU2 left charged and U1 charged. Left-handed lepton doublet and the quark left-handed doublet, right? So here's the left. Let's calculate the left-handed lepton doublet, right? So there are 3 of them, each corresponding to a generation, right? So here's a left-handed neutrino part of the Majorana, left-handed electrons, EMs, right? And they transform under 1, 2 minus half. 2 doublet is, these are leptons, so they are color blind. They are fundamentals of SU2, and they have hypercharge minus half. Well, it's very easy to calculate. This is the half. You just have to, you get a minus half, the hypercharge, trace of Q, for each of the things that are running. There are 2 of them running, so it's 2 times minus half divided by 2. It's minus half. That's the anomaly here. Now, that's not on its own right a problem. You'll have to calculate the same answer for quarks and add them up. So the right, the quarks that run in the loop transform under 3, 2, 6. So you have half 1, 6 times 2. Here is for the doublet of SU2, and you have a 3 is a color index. There's a half. Now, this calculation that I did, both quarks and leptons, they should be multiplied by 3 for the generation numbers, right? But it won't matter because it comes out as a total number. So this is also an anomaly that doesn't vanish, but the total anomaly vanishes. So Stano model doesn't have a 1, 2, 2 anomaly. Good. Questions? Similarly, you can check that the 331 anomaly vanishes, 333 anomaly vanishes, and all of these guys vanish. Important point, the anomaly cancellation of Stano model uses non-trivial relations between the matter, about the matter content. So that is important for the internal consistency of the theory. Good? Yeah.
What do you call it? Since you finished basically going over the previous part,
Right.
previous lecture, I had one question.
Yeah.
So, when you said that you till now we discussed only gauge anomalies, so to say. What about global anomalies? So for those, I presume that even if they're anomalous, it's not a problem for the consistency of the theory.
Yes, it just means that the charge is not conserved. Yes, global anomalies are just global anomalies, right? This is some sort of symmetry, classical symmetry that's violated quantum mechanically.
Is there like a general how do you call it? Is it that very important physically?
What is?
That global anomalies. Like what's the importance?
Absolutely, they're very, very, very important. What was that saying?
What's the importance?
Well, symmetry. Just let's go back to the principles of quantum field theory, right? What were the principles? One of the principles was locality, symmetry, right? If the symmetry is not there, that's an important thing. But these are not symmetries that are not present. They are symmetries at the classical level. They are violated due to loop correction. So the violations are H bar suppressed. They could still be used to understand the theory. There's a long story of anomaly. But I'll actually give you an example of like anomaly physics that you already know. Yeah, but conformal anomaly is a very, very important thing. Yeah, conformal transformations are space-time transformations, right? So there are important symmetries. They're honest to goodness symmetries. They're not gauge transformations. They're space-time transformations, and they could be anomalous. Not the Poincare group, the conformal. We discussed why the Poincare group cannot be anomalous. Do you guys remember this? We went through this long time ago in QFT1. Yeah. It was the issue of central extension. These are the same issues. Here I'm presenting anomaly from a different angle. All right. Any other questions? It was a story of projective representations, quantum mechanics allows for projective representations, all of that. Any other questions?
The central extension.
So we discussed this in QF1. I will discuss this again next couple of weeks. So it's a statement about representation here. Something about representation.
Right, that's another question. So if we see that global anomalies, sorry, global symmetry, the violated quantum mechanics, it's symmetry anomalous, then can we, what do you call it? Then does it make sense to not add those global anomaly, the global symmetry violating terms from the Lagrangian from the onset?
Well, okay, so when you have global, when you compute global anomaly, what you're learning, well, remember the Wigner theorem. If you have a global symmetry, it's represented on the Hilbert space as a unitary or an anti-unitary. Now, what global anomaly is says that you calculate exactly how the transformation works, but it's not a unitary. So you know the transformation. We calculate how it transforms. It's not a unitary. There's a residual term. There's an extra term. It's not a unitary transformation, but it's a transformation you can calculate and control. Good. Did I address the question?
Somewhat.
Ask again.
I'll have to think about it and then I'll ask.
All right. Okay.
Better.
Anomalies are not, they're not like explicit violations of symmetries. Symmetries that are explicitly violated at the classical level, there are just so many ways for them to be violated. Here, the violation is due to quantum mechanics. The violation is fixed by your matter content. There's no freedom, right? Like left for you. For example, we'll just say in a bit that beta function of QCD could be viewed as an anomaly. I'll comment on that. Remember, QCD was a classically scale invariant theory. Why? Exactly. So the fact that it has beta function, it's a scaling symmetry, was a global symmetry of the theory, classically, that was violated quantum mechanically, and we calculate the failure of this to be a symmetry quantum mechanically, and that's called beta function. For global symmetry called scaling symmetry. So they're calculable. They are to be thought of as like the same level of importance as beta function. All right. Any other questions? All right, so now we start the discussion of today's lecture, anomaly inflow. So we said that a gauge theory that's anomalous is bad. It's an ill-defined theory as a quantum theory. If you want to construct a Hilbert space, all of that is bad. But let's just not right away discard it. Let's just keep it in the game and see what we can say. There is a notion called anomaly inflow. So for simplicity, take QED2. It had chiral anomaly in 2 dimensions, right? QED, massless QED had chiral anomaly in 2 dimensions. Take that theory. The theory is not healthy, but we're going to consider it as the boundary of a 2 plus 1 dimensional theory, the bulk theory. So you have some sort of 2 plus 1 dimensional manifold, whatever it is, it could be flat space or whatever, it doesn't matter. The metric, it doesn't matter. It's just flat space quantum field theory. So there is some bulk theory, there is a boundary. The boundary is 1 plus 1 dimensional, so we're going to put on the boundary this theory that is a gauge theory, but it's anomalous. Now, the gauge theory, the action, when I say put the theory, I just mean that you formally write down the path integral, right? And the action. This gauge theory, you could extend it to the bulk. You could think of a 2 plus 1 dimensional gauge theory that has as a boundary this 1 plus 1 dimensional gauge theory. Turns out that the calculation of anomaly on the boundary could be captured by bulk effective action. It's called Chern-Simons action. So what is that action? It's A mu del, oops. is integral of d3 of x epsilon mu lambda a mu del nu a lambda. So a wedge dA. This is a bulk action. In the bulk, I have three-dimensional gauge fields. What's the action for that? Minus 1 over 4th F mu nu F mu nu. This is a gauge invariant term I can add to the bulk action. It's topologically invariant. A wedge dA has no notion of the metric. I can add it to the bulk. Now let's see what happens. This is topologically invariant. Sorry, this is a gauge invariant term in the absence of a boundary. Because remember, every time we're making a gauge transformation, there was a boundary term that we're just dropping out. Let's not drop that out. So what are we saying in anomaly inflow? We say the following thing. Take 2 plus 1 dimensional gauge fields in some gauge fields. Add this Chern-Simons action. Once you add the Chern-Simons action in the absence of boundaries, this is a gauge invariant theory, it's a sensible theory. In the presence of a boundary, the gauge invariance is spoiled. The boundary term, due to the sum of Chern-Simons and the regular kinetic term for the for bulk gauge fields, is precisely what can calculate the anomaly of the boundary 1 plus 1 dimensional gauge theory. So here we're not discussing a quantum field theory on the boundary, Hilbert space, all of that, and the bulk Hilbert space, all of that, right? Here I'm making a statement about path integrals and these calculations. What we did was that we took gauge theory in the bulk, added this Chern-Simons term, because we can, it's gauge invariant in the absence of boundaries. Once you put a boundary, it's no longer gauge invariant. The anomaly term is all a boundary term, and it's precisely the 2D gauge anomaly we just calculated. I just said this. This is QFT2. We're reaching the end of the semester, so I'm just giving you hints towards all sorts of different directions where quantum field theory research goes, right? But when I say quantum field theory research, I mean like in the 70s. Good.
When you say that we saw that anomaly was a boundary, anomaly was like, for example, in D equals to 4, like D equals to 4, that was like just the epsilon, what we F pressure.
Yes.
But that's still defined. It's not entirely like it's a thing we look on at each point. Inside.
From the point of view of the boundary term you're talking. Or no, sorry. What?
So the anomaly the real thing was F pressure.
Yes.
It's defined at each point.
On the boundary. So we were doing a calculation. It was in 3 plus 1 dimensional quantum field theory. We calculated the anomaly term. It came out as F wedge F. Right? That's a 4-dimensional calculation. Now I'm saying, take that theory. We said that theory is safe, blah, blah, blah. Take that theory. Think of that as the boundary theory of a 5-dimensional theory. That 5-dimensional theory is going to be 5-dimensional gauge fields, the standard kinetic term, plus a 5-dimensional action called Chern-Simons action. Right? Is A wedge dA from coefficient. Right? Now, this bulk term, this bulk theory, once you vary it, it's no longer gauge invariance in the presence of a boundary. The correction to it is all a boundary term. What spoils the gauge invariance is a boundary term, and that is precisely the anomaly of the boundary theory. Right? Good. Gauge Chern-Simons theories exist only in odd dimensions. Chiral anomaly we calculated was only an even dimensional concept. Good. So 2-dimensional chiral anomaly is related to 3-dimensional topological theories, Chern-Simons. Okay, Now, an important thing. Imagine you're sitting in the bulk, right? So, sorry. If you have the bulk fields, you have the kinetic term for the gauge fields, like F mu nu squared, right? F mu nu, the standard thing. And then you have the Chern-Simons term, right? Why am I just looking only at the boundary term of Chern-Simons? In principle, there's another boundary term coming from the other theory. It's a sophisticated question. You have all the tools to answer the question, but it's a very tricky, it's a difficult question. The reason is this. Under the normalization group, it's easy just by simple dimension counting. You can see that Chern-Simons theory is more relevant than the standard kinetic term. It's first derivative. It's first derivative, right? Yeah, I said what I said. So in log, first derivative means 1 power of momentum, whereas 2 derivatives is the standard kinetic term is p squared. As you go to low p, the Chern-Simons theory wins. That's why every time people are talking about topological order, they're talking about low energy states of matter, right? In the low energy, when everything, you have gone to such low energies that you don't see, like the only thing that remains, if the theory is gapped, you don't have any local degrees of freedom left. All that you're left with is topological theory. Anyway, that's a sophisticated comment in case you want to relate to. All right. Okay, now let's switch gears and talk about scale anomaly as an example of a global symmetry that's anomalous. All right. So let's start. Consider free massless theory. For simplest case, free massless real scalar field, del mu phi squared. This is classically scale invariant. Actually, as a matter of fact, invariant under the full conformal group. Hopefully remember this. We discussed this last semester. I will review a lot of that. There is a conserved current associated with this. This is another charge for it. What's the conservation law? Del mu of J mu scaling has to be 0. Del mu of J mu scaling, we derived this last time, is the T mu mu. The trace of stress tensor has to be 0 classically so that they have classical invariance. Quantum mechanically, if it's 0, then there's no scaling anomaly. Whatever sits on the right-hand side of T mu mu, quantum mechanically, is anomaly, scaling anomaly. Good. What's the dimension of T mu mu? What's the dimension of T mu nu? Stress tensor. That's easy to answer. What's T00? Energy density. What's the dimension of energy density? Space-time dimension, D. D, space-time dimension, right? So here's one important lesson. Stress energy tensor is always a dimension D operator in the theory. Always. Right? Why do I say it's always there? Quantum mechanically it's always there. Why do I say that? It's a conserved current associated to what transformations? Poincare. So Poincare better be a symmetry of the theory, and it better be non-anomalous. Why? There's no central extension, right? So stress tensor is always there, always, right? It has dimension D, and it's not corrected. The dimension is not corrected, right? There's no anomalous dimension for stress tensor. Last lecture we gave another example of a an operator that's quite often there. If you have a global symmetry, or if you have a gauge theory, let's say you have a gauge theory, you have the current associated to that. What's the dimension of that?
So current was D minus one.
D minus one. You have an operator that dimension D minus one in your theory. So remember in quantum mechanics, when we calculate scaling dimensions, these guys just depend on the coupling, on the scale, they run all sorts of crazy things. But these, when you have symmetries, these dimensions are protected. If you have an honest goodness symmetry, the dimension of the current is D minus one, stress tensor is D. These are integers like 4, 3, right? They don't change. You should always keep that in mind. Yeah.
Yeah, as you were saying, if we have a symmetry, then the dimension of the current is protected. But if we have an anomaly, now the quantum mechanics, the symmetry is broken, then the dimension of that current should change,
No.
right?
Well, when it's broken, right? What happens? All right. We just did an example of this, right? Chiral anomaly. What came out of this? The dimension of this remained D, right? But the conservation law, this plus some operator dimension D became 0. Right? Now, we didn't prove that it's always going to be like that. But at least in the examples we've discussed, this is the setup. But another example that we're going to discuss right now, T mu mu. The dimension of this is going to be D. But you can have scale anomaly. Means that this is equal to some operator that's dimension D. Right? Good. Now, all right. You have a scale invariance, classically, for this Gaussian fixed points that is massless Gaussian fixed point, massless scalar field. You could explicitly break this symmetry by adding terms to the Lagrangian, right? That are GI-OI for some operator OI. And it will explicitly break scaling symmetry if GI has dimension that's not 0. But what if GI has dimension 0? This is a dimension counting marginal deformation. A classical marginal deformation. Right? Now, if it actually gets beta functions, right? If this is not respected, this scaling invariance is not respected quantum mechanical, which means that beta functions of these guys are non-zero. That's just nothing but the calculation of scale anomaly. Good? Click. So the simplest example of this calculation that we discussed in detail is the beta function of QCD or Yang-Mills. Whoops. Uh-oh. What? All right. I'm not sure if somebody was online. Sorry? The recording is on. Yeah, we're good. The beta function of QCD or Yang-Mills, right, was a calculation of this type. Why? Because the Yang-Mills action was classically scale invariant, right? So that calculation, we could just call it what we did. We would call that the calculation of scale anomaly at one loop. That's what we've calculated. It's a global symmetry, so you have done already a calculation of that type. Good. Now, in principle, just by dimension counting, T mu mu has to be a sum as an, this is supposed to be a supposed to be a quantum equation. It has to be a sum of beta functions. These beta functions are dimensionless, right? It's just because it's telling you about the running of a dimensionless coupling. This has to be a sum over marginal operators. So what it tells you is that under the normalization group, if you have a marginal deformation, operators of dimension D will mix. but they won't mix with operators of different dimensions, right? There's a lot of subtlety. There are lots of subtleties here that I'm hiding, but yeah.
So if I remember, we saw that, for example, 6 level company could, so. And contributed me, for example.
Mhm.
And then more.
Mhm.
So. You can like have.
Those have to do with explicit violations. That wasn't scalar field theory.
Scale.
Scalar field theory was what you were calculating was not at all scale anomaly. Those had to do with explicit violations of scale invariance. Because if you sit at the fixed point, nothing's gonna run. You have to explicitly go off of the fixed point, then things run. But that's not at all scale anomaly. The thing that was special about gauge theory was that it was scale invariant. The classical action was scale invariant, but quantum mechanically was running.
Still staying in the fixed.
Yeah.
Yeah, you said that there will be some certainties, what I don't understand why, because if I'm speaking of the running of dimensionless couplings, my dimension of beta will always be zero. So this field, I mean, phi should have the same dimension as T mu, which is D. So how can it have fields of different dimensions?
There are subtleties. There are let me not get into it. There are subtleties. Yeah. Let me not get into it. So in QED4, whoops. Is this what I wanted to say? No, that's not what I wanted to say. Forget about this example. Actually, yeah, maybe I want to say that. Oh yeah, no, that's what I want to say. That yeah. Right. That's what I want to say. If you what the calculation. My hesitation is that the theory is not well defined, right? So you have to look at it's not a genuine tracking theory, blah blah blah. But at the level of the action and manipulation of path integral, these statements are correct. Right? Good. All right. Okay, now we are, yeah, question? We are done with the discussion of scale anomaly. We're gonna wrap up the discussion of anomaly, but I want you guys to understand that all the story that we discussed was so far has been Lagrangian formulation quantum field theory, right? We've been using action formulation. Now, what we ended up was we realized that quantum field theory could be understood as a deformation of a scale invariant theory. So you do standard perturbation theory, right? For you, if you have a way of understanding non-trivial fixed points, then you could just organize your operators, you deform them, and do what is called conformal perturbation theory, right? That's what we're gonna move towards. But before that, we have to understand what conformal field theory is. And can we construct conformal field theories that are not free, right? This is the program, yeah.
So you just go.
Yeah.
So like, so you have one theorem, which is beta G F squared.
Yeah.
But like you could also have epsilon mu times C squared.
Correct. Oh, sorry, this is schematic. When I write F mu nu squared, I don't mean F mu nu. That's not what I mean. I just, that's schematic. It just means that, I just mean that something that is second order in F mu nu.
Yeah, but I was saying that you have a limit in F mu epsilon mu times C squared, like the
In four dimensions or?
oh, that's not.
No, this is QED4.
Yes.
This is QED4. Yeah, you're right in QED2.
Yeah, this is the only equals to four, like you mentioned.
Yeah, well, okay, so sorry. What you're saying is that this is equal 4. That's what you're saying. Okay, good. Yes, thank you. Good. So operator product expansion, OPE, we're gonna briefly discuss it to just try to, it's going to be about a different way of thinking about conformal field theory. Sorry, about quantum field theory. And it hopefully includes interacting theories. Turns out that all the theories that we're not gonna get as a whole course, it's like we spend the rest of your life studying conformal field theories. But turns out that almost all the examples we're gonna construct at the end of the day that are rigorously constructed, we also have the Lagrangian relations of them, with a few important exceptions. But those theories are not really constructed. We have evidence that they exist, blah, blah, blah. Yeah.
So just to close this scale anomaly, so how do you formally define scale anomaly?
How do you formally define scale anomaly? Well, what is scaling transformation? If you have a theory, right? Every theory has an effective action. Expanding H bar. If the H bar going to zero limit of it has a symmetry, which is violated by the other terms, that's called scale anomaly. And then scaling symmetry, that's by the way, by other terms, it's called scale anomaly. Right? That's one way of saying all of this. But another way of saying is that if the hypothetical measure violates scaling.
And why are we saying it depends on the matter content? Because the corrections come at the quantum level of loops. The terms of this.
Because the quantum corrections are about loops, and what runs in the loops depends on the matter. Or whatever field you have whatever your matter content is, you path integrate over those. And each of these guys contribute to a certain amount, and they could add up and cancel.
They are suppressed by H.
Yeah. Now, here at this level, all right, do I want to make this statement or not? When I talk about cancellations, already you should feel that there is something topological about it. Numbers that are like 2, 1, you add 2 of this, cancels with that, right? If you could just add a couple of these fields and a couple of those fields that they cancel like 0, it means that what you were dealing with in the appropriate unit was a bunch of integers or rational numbers. A bunch of this canceled with like 15 of this canceled with 17 of that, right? So these are not really continuous numbers you're dealing with. Anyway. All right, so we're gonna completely switch gears. Any questions about anomaly? Ooh, I'm really behind. So no questions. I don't make any questions. All right, so let's go back to quantum field theory. In quantum field theory, QFT1, we said we're gonna organize the fields in terms of EREFs of Poincare group. Why? Because those were our particles, right? We said quantum field theory, that's the notion of particle we have. In D equal 4, represent what's the Poincare group in D equal 4? Sorry? Just say it. What's the Lorentz group in D equal 4? That's O3, 1. And then Poincare group is this. Yes. Okay. Awesome. Now, the way we constructed this was through a Lie algebra that we saw was the complexification of we saw was 2 copies of SU2. Right? So there was one way, and the representation of SU2, hopefully, it was just a standard thing, right? But when we discuss this in at the high level, so what I'm doing is that I'm building up towards the representation of Lie algebras. I want to give you a little bit of picture, like some picture, and now I'm gonna move back to this to come back onto the earth. But a lot of what I say is all over the place in quantum field theory models, right? So representation here we're organizing in terms of spin and mass. These were simultaneously diagonalized, right? So spin and mass. Was mass an eigen m squared was an eigen operator of what? Eigenvalue of what operator? P squared. Awesome. What is spin an eigen operator of? Let's say your m squared is non-zero. Well, actually, I don't even need to say that. What's the spin an eigen operator of? All right, I'm gonna say that. I'm just reminding, right? So take what was important about p squared. P squared under Lorentz transformations. Well, first of all, p alphas, p mu's can mu to p squared. That's obvious, so they won't change it. Lorentz transformations, SU3 comma 1 will leave p squared invariant. You move in this hyperboloid, right? So that's good. Now, imagine your particle is massive. So you have a rest frame. You go sit in the rest frame. What symmetry do you have? You have the little group. The little group is a subgroup of Lorentz transformations or Poincare transformations that leave P mu unchanged, right? So it's lambda mu news. Of course, this part of it leaves the whole thing leaves P mu unchanged because it's a billion, right? It's a subgroup of the Lorentz group that leaves P mu unchanged. The physical picture I gave you guys is that go sit in the rest frame for massive particle where there is a rest frame. Go sit in the rest frame of the particle, and what is left? What is the symmetry that's left for you? Rotation, and that's a little group. What's the rotation group here? SO3. That's it. SO3 representation theory is organized in terms of its complex, complexification, cover SU2. It's basically you're dealing with SU2. That's the spin we are talking about, right? So always keep in mind, spin is coming from this little group, and p squared is p squared. MNS, right? So you know how to explore different S's, right? This is the standard representation of the SU2. How do you change p mu? Translation P mu to p mu. Boost. Boost. Good? All right. Okay. So SZ is the little SZ is like the label that tells you the representation of SU2, right? And P mu is you change it using boost. There's always the lowest weight representation, right? Where P mu is 0, and then you add to it, right?
Is there any specific reason to quantize the spin around Z? In the region?
No, there's no quantization going on here. We're looking at unitary representations of this group. So now you can call that quantum.
Just
These are unitary representations. Now, what do you know about unitary representations of whatever? No, I'm not going to bug you with that. Just one important you know unitary representations of SU2 that are finite dimensional. Can you have unitary representations of Poincare group or Lorentz group that are finite dimensional? No. Why?
It's not compact.
Non-compact. The keyword is non-compact. Here, SO3 is compact. Good. I was initially thinking I should probably take 2D Poincare group where it could be super explicit about all of this without like going through a headache, right? But I thought like it will be a detour. It will be a whole lecture. All right. So conformal symmetry. If you have a conformal field theory, the principle is the same. You have to look at E reps of the conformal group. And turns out that the conformal group is a space, these are space-time transformations, right? What do you have on top of Poincare? What extra generators do you have?
Inversion.
Yeah, but like, so let's just first talk about scale symmetry. You have dilatation. Can you add dilatation without inversion? Do you have a scale invariant? Oh, we went through this. All right. Well, there was an EJ, do you remember? Okay, you go back to your notes. I'm not gonna tell you. But anyway, what extra generator do you have in conformal group? Special conformal transformation. What's special conformal transformation? What's the simple way of describing? Invert, translate, invert back. right? So it's only an inversion that's been really added. Now, inversion was a tricky thing. It didn't, what did I, whatever, I'm not gonna, yeah, okay, good. So we're gonna be looking at the representation theory of conformal group. It turns out to be it's very large, right? It turns out to be very constraining. What is the conformal group in? All right. R d comma 1, or sorry, d minus 1 comma 1. What's the Lorentz group? Just what's the conformal group? Sorry, what am I
D
saying?
minus one comma one.
Yeah, d minus 1 comma 1. Yeah. What's the conformal group?
SOC comma.
SO. Right? Now, this is Lorentzian theory. Oh, I did this so poorly. R D Euclidean. What is this group? What is this group? SOD plus 1 comma 1. Am I making a mistake? Yeah, I am making a mistake.
Yeah.
Yeah. Yeah, I'm making a mistake. Sorry about that. Good? All right, good. So an important lesson. If you wanna do the representations here of conformal group, Euclidean conformal group, you have already done it. It's a Lorentz group. So you know exactly what it is. How do dimensions work? If you're interested in so what is the one that you have done really, really well? SO3, 1. Which Euclidean conformal group is that?
R square.
Equal to. So Euclidean two-dimensional quantum field theories. So you wouldn't be surprised that the representation theory of that is organized in terms of mass and spin. It's a little bit more nuanced than that, but we're gonna go through that. All right, good. At least it should be something familiar. It's not quite mass and spin because that was a Poincare group, right? Lorentz group, we went through the representation theory of it. It was two copies of Good. But it is related to that language. All right. So what I'm gonna do in the remaining 10 minutes or so is I'm gonna review a little bit or hopefully it's not too new. I'm gonna review a little bit of Lie algebras to set this language, and then next week we're gonna start doing conformal group and representation theory and work towards conformal field theory. What I'm gonna go over now is extremely useful in physics. In what sense? Pretty much almost all examples of quantum field theory we have honestly constructed go through Lie algebra constructions. The principle is very simple. If a theory doesn't have much symmetry, we've seen it all over this course. If it doesn't have much symmetries, it's just hard to control it to keep it well defined as an interacting theory in the IR, right? We saw that the theories that we had good control over had tons of symmetries. And those are the theories we could explicitly construct. We can show actually that they are interacting in infrared and we can calculate with them. So you wouldn't be surprised if we use symmetries. What is nicer than a Lie algebra or a Lie group, right? So a lot of these constructions go through Lie groups. So I'm just gonna review that. What is the Lie algebra? So Lie group is like exponentiated version of the Lie algebra. Lie algebra is the tangent, right? Lie group was this topological space, blah, blah, blah. It's a group, this topological group, all of that. We did go over it. So a Lie algebra is a vector space. It's a tangent space to a Lie group with this funky slash mathfrak G. A group with an antisymmetric bilinear operation that is called a commutator, right? Once you realize a representation, what's the representation of it? It's just that you realize these as matrices, some vector space, right? A linear representation. It's a map from, it's a bilinear, so it takes two vectors and pops out the vector. Right? It's an anti-symmetric bilinear commutator. It satisfies the Jacobi identity. That's important. Good. Now we said every Lie algebra can be specified using a set of generators, and the generators will satisfy these relations. Those constants are structure constants. They define the Lie algebra for you. The number of independent generators is the dimension of the Lie algebra. These ABCs are structure constants, and we pick them to be real. Well, these are FABCs are real if JAs are self-adjoint. Why would you want self-adjoint ones? Any guesses? Unity representations. Right? Good. Got it. So every time there's that every single time confuses me. Where you put the I is important. All right, good. So here we're talking about self-adjoint generators. Well, yeah. Any questions? A Lie algebra is simple if it has no proper ideal. That means that what's a proper ideal? Having no proper ideal, it means that there's no subset of these generators that rotate among themselves on their commutation relations. Meaning that if you just take a bunch of them on their commutation relations, you get everywhere. You generate everything. Good. That's the absence of a proper ideal. That's called a simple algebra. A semi-simple algebra is a direct sum of that. A bunch of simple ones. Right? You just have a bunch of blocks that within each other, they transform to each other. Good? Got it? So that's what a semi-simple algebra is. We're going to be talking about semi-simple algebras. Now, in whatever number of minutes we have left, all I want to tell you guys is something you've seen over and over again, and you will see over and over again until eternity, as long as you do physics. This Cartan-Weil basis. The way we're going to construct a representation theory of some sort of non-abelian algebra is by first step, always find a maximal set of mutually commuting generators. And the discussion we just had, what was that, those generators? It was we just diagonalized this and m squared, right? P squared and the load, right? That's important. But you're familiar with this in like quantum mechanics all the time, right? Like conserve charges, just diagonalize them, right? Simultaneously. So these are those guys. The maximal is important because if you don't pick the maximal group, maximal abelian subgroup, you're doing something not efficient. Now the maximum, of course, the dimension of it has as a number r. It's called the rank of the Lie algebra. Good. All right. Is this familiar? So the abelian subalgebra, the maximal abelian subalgebra, has a name. It's called the Cartan subalgebra, and it's this mass frac H. The remaining generators, we're going to organize them in terms of raising and lowering operators. So in your head, this is how you should think of this. This is a generalization of simple harmonic oscillator. H is the number operator. E alpha is a bunch of them. There are a bunch of them, right? Let's say you just have one of them. Is in this case annihilation operator. Sorry, creation operator. Is a creation operator. And this is called the root. Tells you when you add with this creation operator, how much energy you add. And the standard AA dagger algebra, that is what? In quantum field theory of free fields. Just omega. A omega adds a mode with energy omega. Right? These are called roots, and they carry a label because there are a whole bunch of them. Right? These are called ladder operators, not surprising. And again, not surprisingly, these ladder operators are not self-adjoint. They're like creation and annihilation operators. And E alpha dagger could be viewed as E minus alpha. I'll say in a bit what that notation means. But for now, let's just go. Why am I doing that? Okay, let's go through. I had coffee, that's why. So imagine you have an eigenvector of these guys. Eigenvector here I just mean because they're simultaneously diagonalizable. I can put lambda 1, lambda 2 to lambda r, because there are of these guys, rank of them, right? So there are of these guys, and these are the eigenvalues, simultaneous eigenvalues. Now, if you act with one of these E alphas in lambda, this is an eigenvector with this eigenvalue. Good? Got it? All right. Roots are non-degenerate. Why? First of all, now what does non-degenerate mean?
Two A alphas can have the same value alpha.
Yeah. Why? Because if they are degenerate, it means that by changing your variables, it means that you found an E alpha such that commutes with all HIs. But then that means that you didn't pick the maximal abelian subgroup. Right? Because HI is the Cartan is the maximal abelian subgroup, alpha I is always going to be non-degenerate. The roots are non-degenerate. All right. So what do we have so far? HIAJ, they commute. HIE alpha, they satisfy these raising operator convention. The dagger we call minus alpha. Now let's collect the set of all roots. These are a collection of these alpha i's. Right? Good. Let's calculate the following object. So what we're after, because I have these relations, the only thing I'm missing is the commutator of E alpha E beta. That's all I need to say I know everything about my algebra. So first thing is I realize that just using the commutation relations, I have the commutator of E alpha E beta with the commutator with HI looks like this. Good. Now, if alpha plus beta is inside the roots, then this relation holds for some numbers and alpha beta. That's maybe it takes a line or two of algebra to convince yourself of that. If alpha is minus beta, you're basically looking at the commutator of A and A dagger, right? This is going to be 2 over alpha squared alpha dot H. Okay. Otherwise, E alpha E beta, they commute. All right. We're out of time, but a good example to go through this, maybe I'll do it next week, is 2D Poincare group. Actually, two-dimensional chiral half of Poincare group is as easy as it gets. But yeah. What are the generators of 2D Poincare group? Just say it loud. So it's SO1, comma 1, direct semi-direct product of R1, comma 1. R1, comma 1 is translations, right? So pick 2 translations, null translation in this direction, null translation in this direction, right? What other generator you have for SO1, comma 1? What's SO1, comma? What's the Lorentz group in 1 plus 1? Just boost. Yeah, just boost. So you look at the following algebra. You have boost, null translations, null translations. Look at this algebra, work this out, It's super easy. And you see all the structure. Good. All right. Finally, let me just say I'm running out of time. In conformal field theory, the conformal algebra can be put in the same form. By the way, this is the Jordan form. If you're familiar with matrices, what is A and A dagger in the energy eigenbasis? They're ket n plus 1 raw n. So there are these in terms of matrix algebra, there's 0, 0, zeros, 1, above the diagonal, one below the diagonal for the dagger. This is the Jordan form. Right? Good. This is the generalization of the same principle. Nothing really fancy. I mean, at the end of the day, these are matrix algebras. There's nothing crazy going on. All right. The Euclidean conformal group is SOD plus 1 comma 1. It's the same as the Lorentz group. We're gonna label them using simultaneous labels of spin and scaling. Scaling here plays a role of that p squared. The eigenoperators of S, eigenvalues of this is the scaling dimension, and this is the spin. Now, you go back and think about conformal field theory in the Lagrangian formulation. This is literally what you could do, right? Minus half del mu phi squared. This is an operator, what spin? What's the spin of this operator? 0. It's a scalar field, right? Spin 0. What is the scaling dimension of it? D minus 2 over 2, right? Take fermions, take all sorts of free fields, right? You could play around with the spin, the dimensionality and all of that. Good. All right. Now, okay, this is scaling. This is spin. The raising and lowering operators are P mu is the raising operator. K mu, special conformal transformation, is the lowering operator. We're going to do this later, but the lowest weight operators, in the lowest weight representation, which comes from diagonalization of delta, the D scaling operator, they're called quasi-primaries. By acting on P mu, they're like annihilation operator, creation operator. You just add excitations. And you make what is called a primary module. An infinite dimensional vector space. Just you keep adding, right? Why is it infinite dimensional? These are unitary representations. They better, and these are non-compact groups, right? It's P mu. Better be infinite dimensional, right? I absolutely encourage you guys to do this for two-dimensional Poincare group. Actually, even simpler than that. Let's say your theory is a chiral half. So all you have is boost restricted to this line, which is scaling. What is boost? Is x del t minus t del x. You write it in this notation is x plus, well, sorry. Yeah, it's just basically scaling. It's just scaling. And it basically sends x plus to e to the power lambda x plus. So you have scaling, you have translation. That's your whole group. Well, you have inversion as well. You'll figure that out. So just work a chiral half of 1 plus 1 dimensional free fields, and you get used to this representation theory. You will learn what these derivatives are doing for you. Good. Any questions? I know this is really quick, but we have no choice. Any questions? So what did I do? I went very, very quickly through, well, we reviewed anomaly, chiral anomaly. We talked about scale anomaly. We talked about beta functions for dimension counting, dimension counting marginal operators as scaling anomaly, right? Then we started talking about the Lie algebra representation because conformal group is what we're interested in. So Lie algebra, we're going to organize everything in the representation theory of this group, right? It's always this in the form of this lowest weight representation, and the structure to have in mind is always the same. You'll have an operator, in this case, scaling operator, and spin. They're simultaneously diagonalized, right? And then this is what you have diagonalized. Now, on top of this, we generate the whole thing. P mu's derivatives. They're like creation operators. K mu are like annihilation operators. Based on what I told you, what's the definition of the lowest weight? Killed by K mu. Yes. All right. Any questions? We'll come back to this. I'll review this a couple of times. I'm going fast, I understand, but hopefully. Last questions? No? I think your generation probably will get used to quantum filtering this language. Well, maybe the next generation will only hear about this. I don't know, it's not required.